So far I showed you an example problem where we had one optimal solution and then two special cases, one where we had multiple optimal solutions and the second case was when we had infeasible problem and optimal solution did not exist. This is the third and the last special case where in which we will have an unbounded problem, and because of that the optimal solution will not exist. But in this case we will have some feasible solutions. It's just that we will not be able to show which of them is optimal. So let's see the example. In this example problem, a farmer would like to plant watermelons and cantaloupes on his field in such a way that he maximizes the total profit. So again, the problem is of a similar type. He knows how much profit he gets for each acre of field that he plants with watermelons, and the same for each acre planted with cantaloupes. So notice that the unit of measurement here is acre. That's a measurement, that's a unit of area used in agriculture. And the farmer probably is confident he will sell all the products he produces. However, he would like to have certain balance between watermelons and cantaloupes, and he says basically the number of acres of watermelons should be at least as large as the number of acres of cantaloupes. So how do we write this model? We need to decide the number of acres of watermelons and the number of acres of cantaloupes, which can be expressed by variable x1, right, will be number of acres of watermelons. Now some of you might be tempted to just say number of watermelons, right? What would this say? Well, this wouldn't be, the measurement wouldn't be in acres. This would be in actual watermelon fruits, right? And while this kind of variable is okay, you could use a variable like this, it would be very difficult or awkward in this problem, because everything that is given here is given per acre of watermelon. It is assuming that the unit is acre planted with watermelons. There are probably multiple watermelons harvested from 1 acre. So writing it this way, you'd have to try and figure out how many watermelons there are per acre, because an acre gives you $25. An acre of watermelons, not one watermelon, right? And this is actually not given, so it would be difficult, if not impossible, with this information to write a mathematical model. Of course, the correct definition would be number of acres of watermelons, and the second variable would be x2, number of acres of cantaloupes. Right? Now the objective is, of course, to maximize the total profit, which will be 25 times the number of acres of watermelons, $25 for each acre of watermelons, plus 40 times x2. So we can comment here, say, profit in dollars. Now, what are the constraints? The only constraint that is given here in the problem is that the farmer would like to have at least as many acres of watermelons as cantaloupes, as acres of cantaloupes. So you see that this means that he wants to have, we'll say, subject to number of acres of watermelons is x1. And he wants this to be at least as large, so that means greater than or equal to, and then to a number of acres of cantaloupes, and that is x2, right? So we have this constraint, and of course now we could leave it as it is, but in linear programming, especially when you try to implement those models in computers, often we need to put constraints in such a way that all variables are on the left hand side. So this constraint, I'll actually transform it, right, into such a version, where equivalent version, which will have all variables on the left hand side. So I can, for example, say x1, and I will take x2 to the left hand side, so it will be minus x2. And once I do this, what will stay on the right hand side? Well, there won't be anything, so there will be only 0, right? So I hope you see these two constraints are equivalent, right? One and the other, this is the same constraint, just written in a different way. So I will keep it like this. Okay. And what are other constraints that I need to include? Well, there's nothing defined in the problem, but there is a natural constraint which we have to include, which we have to say basically that the number of acres of whatever we plant cannot be negative. So we want to say x1 greater than or equal to 0 and x2 greater than or equal to 0, non-negativity, right? So now that we have our model, we would like to determine what is the optimal solution for this, right? What should the farmer do? What is the optimal solution? So let's try and draw the feasible region. So I'm going to first indicate the non-negativities, the last two constraints, which are quite easy, right? They are to the right, that's x1 greater than or equal to 0, to the right of x2 axis, and here above x1 axis, x2 greater than or equal to 0. And now there is what's left is still the first constraint, and this first constraint is as x1 minus x2 greater than or equal to 0. Now for this, of course, I need to first compute where are the points that give me equality equal to 0, right? So I need again 2 points and that satisfy this equality, and I need to draw a line that goes through those points. So if I try x1 equals to 0, what will I get? I'll get minus x2 equals 0. That means x2 is equal to 0, and that means I have a point which has coordinates 0, 0. Now if we try the same method as we used to do before, if I try x2 is equal 0, right? If x2 is 0, then I have x1 is equal 0 from the constraint. Well, that gives me the same point, 0, 0, right? So so in this case, that I still have only one point. I still have only this 0, 0, right? I need another point. I didn't determine a second point yet. I haven't determined a second point yet. So I need to try some other value. Let's say I'll try x1 equals 100. So I plug into the constraint. I have 100 minus x2 equals 0, and that means 100 equals x2, right? So x2 is 100. x2 is 100, and that gives me a point which is 100, right? x1 100 and x2 100. So there is a point that will be somewhere here, right? Now I have 2 points. I can then draw the straight line. Okay, so I've determined where where are the points that satisfy the constraint with equality are, right? Equal 0. Now the question is, where are those points that give me greater than or equal to 0? Is it going to be below this line or above this line? And most of you will not be able to just easily say, well, these are below or these are above, right? So how do we prove it? Again, we have to try. Okay, there are 2 cases possible. Either it's going to be like this, or it is going to be like this, right? One side or the other. Which one is it in this case? Well, we have to test one of the points, and we cannot test the easy point now, the 0, 0, right? Which is normally the easiest one to do the computation on. We cannot test it because 0, 0 is actually a point on the line, so it is feasible, but it is feasible with equality. We want to test a point which is either strictly above or strictly below, right? So what I'm going to try is let's say this point, right? This point is, what is it? It is 0, 100, right? So if I try x1 equals 0, x2 equals 100, I'm testing a point for feasibility, and plug it into this constraint. So I get 0 minus 100 on the left hand side, so that is minus 100. Is it greater than or equal to 0? No, it isn't, right? Negative 100 is not greater than or equal to 0. So what I determined by this is not feasible, right? This is not a feasible point. This one is not a feasible point. So that means it is not the case where all points above are feasible. This is not feasible. That means this whole side is not feasible. That means the points below the line must be the feasible point. So let me now indicate that. Okay, and now let me do some cleanup here. Okay, so we've plotted the three constraints, the lines for the three constraints, and we've indicated which sides are feasible. Now let's ask ourselves, where is the feasible region? Where are the points that satisfy all those three constraints? What is the common set of points? And you will notice that the common set of points are all points here in this area, right? In fact, x1 greater than or equal to 0, this constraint is redundant because it is always satisfied once we satisfy this and this. So in this case, redundant meaning it is always going to be satisfied even if we didn't have this constraint in the model. So the feasible region can be indicated like this. Now what I need to comment on is the boundary on the right hand side. On the right hand side here, this is not a boundary. This is not this is not the side where the feasible region ever ends. In fact, you know, if you go here to the right and then slightly up, right, as long as you stay below this line and as long as you stay above this line, all points that satisfy those two are feasible. So this is never going to end on the right hand side, and we call this an unbounded feasible region. Okay, unbounded feasible region. Sorry, unbounded feasible region. Okay, now this is still not a problem, right? Because it is not a problem that we have a set of feasible solutions that is not bounded from one side. The question is, right, if we have basically a lot of choices, but the question still remains, what is the optimal solution? So we have to now focus on the objective, right? We have to see if we take this objective, maximize 25x1 plus 40x2, where does it get the largest value? Where is the highest profit? So we can try to draw level curves. So I'll try 25x1 plus 40x2. I will try to compare it to, let's say, 2000, right? And so why does it satisfy this? Which points satisfy this constraint, this equality? If x1 is 0, then I'll have 40x2 equals 2000. So x2 equals 2000 over 40, which will give me 50. So this is a point 0, 50, and it lies here. And if I try, let's say, x2 equals 0, then I will have 25x1 plus 0 equals 2000. So I will have x1 equals 2000 over 25, that is 80. So this point is 80, 0, x1 is 80, x2 is 0, and it is somewhere here, right? So the line will be like this. Now, now if I try another value, let's say I'll try 25x1 plus 40x2 equals, I'll double it, 4000, right? If x1 is 0, then you'll see x2 is equal 100. So I have 0.0100, and that is here. And if I try x2 equals 0, then x1 will be 4000 over 25, which is going to be 160. So this point is 160, and it is somewhere here. And now I need this line. So I want to do some cleanup. And now we can see that the objective function is improving in this direction, right? So how far can we move the objective, how far can we move the level curve? right, in the direction of improvement. Is this far enough? No, there are still points that are above. Is this far enough? You might think that's it, this is the optimal solution, but remember what I told you, there is no boundary here. So in fact, just that we draw this line, right, it doesn't end here, that this line goes on, and this line also doesn't end here, it goes on, and the feasible region here on this side doesn't end, it goes on, it continues without limit. In the same way, this line can be moved further, and we will never reach the last feasible point beyond which there are no feasible solutions, right? The region on this side is unbounded, and it happens that the objective function, when we move it in the direction of improvement, the level curve, when we move it in the direction of improvement, we will never stop on the last feasible solution. So by this principle, we will say we will never reach the optimal solution, because that's because for whatever line we try, right, for whatever solution we would like to select, we can always show there are better solutions, right? So you can't say there is an optimal solution, any of those feasible solutions. You can't say it is optimal, because for any of them you can always show there is an even better solution, right? If I try 150, 100, this point here, I will always be able to say, well, there is 200, 100, and I can go to the right and up, and I can improve the profit without limit. So what can we say here? So first of all, what we said before is that feasible region is unbounded. But this is still not a problem, right? The problem is that when we test the direction in which the objective function improves, we see that the objective function moves in the direction, improves in the direction in which there is no bound, okay? So when we tested the improvement of the objective, when we draw the level curve, we see that the improvement is in the direction where there is no bound, and because of this, right, the problem is unbounded. We say the problem is unbounded. Okay, the problem is unbounded because the objective function can be improved without the objective function value can be improved without limit. Okay, so in this case, what we say, if the problem is unbounded, optimal solution does not exist. Optimal solution does not exist because we can always show, for any solution we choose, we can always show a better solution than this one. Now, two comments. First of all, what does it mean in practice? What's wrong here? Why isn't there an optimal solution? Can't this farmer do something? Well, in fact, it often indicates in practice that there is a mistake somewhere. Either someone forgot about a constraint, or some constraints are incorrect. Well, in this case, the easy explanation is that the farmer probably has a limited size of the field, right? And he forgot to tell us, and we forgot to ask, right? For example, if he says that he has, let's say, 150 acres, right? The field is 150 acres. Okay, if this was the case, we learn that it is actually 150 acres. Then we will discover, well, then that means we can't plant in total more than 150 acres. So x1 plus x2, which is total number of acres planted with whatever, is at most 150, and that would add a constraint here, and you could solve it, and you would see there is a solution, right? So this is, in practice, an unbounded problem is an indication of a mistake somewhere in the modeling process. Second note is that you might think that when we have unbounded feasible region, it will always mean an unbounded problem. It is not always the case. For example, consider what would happen if we had an objective here, if the objective was not maximization but it was minimization, right? It doesn't make sense in the profit, in the case of profit, but imagine that it is not profit but something else, and we're minimizing it, right? And this objective, of course, would have the same level curves, but the improvement wouldn't be in this direction. It wouldn't be this direction. It would be in this direction, right? If we minimize, okay, we would like to decrease the value, and in this case, this would be the optimal solution, this corner point, right? So when you have feasible region that is unbounded, it doesn't mean that the problem is unbounded. We still have to check the direction of improvement according to the objective function, right? In our original case, when we maximized, the direction of improvement was in such a way that we could improve without limit. But if it was minimization of the same function, we would stop at this corner point, and the problem with feasible region unbounded would have a solution. So the thing to remember is, when you have a feasible region that is unbounded, you still have to see the objective function to decide whether the problem is unbounded or whether the problem has an optimal solution in one of the corner points. And this is actually also why, in this case, I do not recommend using a corner point method, because when you enumerate corner points, you will not see the case of unbounded problem, right? If I try to enumerate in this with minimization case, if I try to enumerate all corner points, what are the corner points here? This feasible region has just one corner point, this one, okay? There's no end here and no end on the horizontal axis, so there are no corner points. So in this case, we would see there is only one corner point, and that by this has to be the optimal solution. Well, if the objective function improves in the direction of this corner point, then yes, it will be an optimal solution. But if it happens to improve in the direction in which there is no bound, then the optimal solution does not exist and the problem is unbounded. So thing to remember, when you have in feasible region unbounded, don't use the corner point method, use the level curve method. That's all about the last third case, special case unbounded problem in linear programming.